officially accepted Technion. Yeah, it's official.
Have you watched any of the lectures in this class before?
I've watched Ilya's lecture.
Oh, Ilya's lecture.
Yeah. I think that was shorter though than
that was last semester, yeah. It's
okay.
a slightly different class, but yeah, here we're gonna have so we have Hong Lak on Wednesday.
Oh.
And we're gonna have Mohammed Narouzi from Brain the week after. And then Kwok talked about his architecture research last week.
Ah.
Of whatever 800 GPUs that they needed.
So you had like formal lectures in the beginning and then invited.
So we had like 2/3 of the class to actually teach the material
Mm-hmm.
and then fun research stuff in the last.
Mm-hmm.
Okay, I think we'll get started now and then. All right, hi everybody. So today we're going to have kind of a last-minute substitution. Unfortunately, Peter Beal was a little bit sick, so we changed the schedule around so that Aviv is going to present actually today, and then Peter will present in Aviv's slot later on in the class. So Aviv Tamar is a postdoc currently here at UC Berkeley. He finished his PhD at Technion, and he'll actually be starting at Technion in a little while as a professor. And today he's going to tell us a little bit about some risk-sensitive reinforcement learning and some newer work on value iteration networks.
Thanks, Sergey. Hi, everyone. So my research is on reinforcement learning. And today I'll talk about two challenges in reinforcement learning, which are safety and generalization. So motivation is that robots today are very good at performing repetitive tasks. For example, in the car manufacturing example shown here. In these tasks, the environments are well controlled and predictable, and the tasks themselves are very predictable. The standard tools for developing controllers to assemble these machines, for example, is classical control theory, which works very well when you know everything about the tasks and the environment. My long-term motivation, however, is getting robots outside of these well-controlled habitats and into places like our homes, hospitals, working alongside humans, unstructured environments. From an industrial perspective, there's also some motivation for this, because currently the classic control theory methods that are being used to develop these assembly controllers take quite a lot of engineering time and can actually bottleneck the time to market in some products. For example, if you're assembling a mobile phone and you're changing, say, a button on your phone, you don't want to invest too much time in redesigning the controller for assembling it. So many people are now looking into methods that can quickly learn to adjust to changes in the product design. So what if we want a robot to cook for us or make our bed? This raises many challenges. For once, we need to deal with unstructured environments that can change in time. The dynamics for tasks like folding a pillow requires dealing with contacts and friction as part of the solution, which means non-linear and non-smooth dynamics. And often, we can never get a true physical model for these tasks. So for example, can you think of getting a physical model for a pillow or for an omelet? And finally, if we really want to get robots into our lives, safety will be essential. We need to provide some guarantees. So at least the first three of these challenges are extremely difficult for classical control theory, which relies on building analytical models of the problem and solving them. So while we can try to push classical control further, many researchers are now looking into alternative methods, which are designed from the bottom up to handle these challenges. And reinforcement learning is one very promising method that, as you know, is designed based on learning how to control the way that humans learn to act through trial and error. The classical model in RL is that the robot can take actions in the world and observe how his actions affect the state of the world. And he also observes a reward signal, which is our way of specifying the task for the robot. And we have machine learning methods that can learn a policy which is mapping from states to actions such that we get high reward, therefore achieve the task. And by basing the control on learning instead of solving analytical models, reinforcement learning is naturally equipped to handle the challenges that we described: unstructured environments, difficult dynamics, and unknown physical models. However, in practice, we still have several challenges left. For example, how do we guarantee safety when machine learning is involved? Also, how can we design policies that can generalize well to changes in the task or in the environment? And finally, how can we deal with high-dimensional states and action spaces, for example, a robot perceiving camera images and outputting motor commands? So there's been recent progress on many of these challenges, and today I'll talk about some of the work that we've been doing, where the goal is to really get reinforcement learning to come through on these types of problems. In particular, in this talk, I'll start with our work on safety through the notion of risk-sensitive reinforcement learning. Then I'll talk about value iteration networks, which are neural networks that are designed for reinforcement learning tasks and can achieve better generalization. And then I'll talk about an extension of that work for continuous control in robotics. So let's talk about risk-sensitive reinforcement learning. But first, let me remind you the definitions and some kind of formal introduction to RL. So as you know, the mathematical formulation in reinforcement learning is a Markov decision process, or MDP. We denote by S the state of the robot and the environment. A is the action that the robot can take. And upon taking action A, the environment transitions to a state S prime with probability P. So P here denotes the physics or dynamic of the tasks. We denote by pi a policy, a mapping from states to actions, and by R the reward. And our goal is to find a policy that maximizes the sum of the expected sum of discounted rewards. Here gamma is a discount factor. And as you know, this is the difficulty or challenge in this formulation is that this is a sequential decision problem. We need to think about how each action affects the states that we will be able to reach in the future, and therefore the rewards that we will be able to get. When we know the model, we can actually compute an optimal policy. This is known as a planning computation. And mathematical ideas here relate to dynamic programming. What we need to do is define something called a value function. Value function for policy pi is just the expected sum of discounted rewards starting from a particular state and following that policy. So it's a function from the state space to scalar values. What we would like to calculate is the optimal value function, the value function of the optimal policy. And there's a dynamic algorithm for doing this. It's called value iteration. The idea is that at each iteration we'll update our values for all of the states by taking the reward at that state plus the maximum expected value of the next state. We maximize over our possible actions. So the intuition for this algorithm is actually pretty simple. Let's assume that we initialize the value function to 0. Then in the first iteration, we'll just update the value as the reward. This would correspond to the first element in this sum. Then in the second iteration, we'll maximize the reward plus expected next value, which is just the expected reward at the next state, corresponding to the first two elements in this sum, and so on and so on and so on. By induction, once we reach iteration k, we would be maximizing the first k elements in this infinite sum, and this would converge to the optimal value function, and it converges in a geometric rate. The theory to show this convergence involves showing that this operation involves a contraction with a parameter gamma, this discount factor. The reason that we calculate the value function in the first place is that it makes it very easy to select the optimal policy once we've calculated this value function. We just need to select actions that are greedy with respect to this value function. So this is cool. We've transformed the infinite horizon sequential decision-making problem into a single-step decision-making, a greedy decision-making actually, based on this value function. Now, what happens when we don't know the model, or when there are just too many states to compute value iteration efficiently? Then we can use reinforcement learning. So there are, as you know, two main approaches in reinforcement learning. The first one is called value function based methods. So here we'd use function approximation, for example, a neural network, to approximate this value function. Here theta would be the parameters of this approximation, for example, the weights in a neural network. And we have sampling-based methods, machine learning methods, to estimate these parameters from data. This data comes from the trial and error or exploration of the robot in the system. Second type of methods are called policy gradient. Here we use the neural network to represent the policy. And we update the parameters of this approximation using gradient descent on our actual objective of maximizing the expected discounted reward. And here we would use sampling to estimate this gradient, again from the trial and error interaction with the environment. And currently, variants of both of these methods that use deep neural networks are currently the state of the art, which is probably the reason that you're taking this course. Now, let's talk about risk. First of all, why should we care about risk? There are two reasons. The first reason is the world, the environment can be stochastic. And in this case, we might want a policy that can generate good performance even if we get unlucky. For example, if there is noise in the world, we might want to guarantee that even if we get a very unlucky noise sequence, our robot will still behave good enough. But in the standard reinforcement learning literature, the only notion of uncertainty is through the use of the expectation, the expected discounted rewards. But the expectation is a very poor account of uncertainty. For example, it doesn't take into account any variability of this random variable. So we can replace the expectation with something called a risk measure. A risk measure is a different statistic of this random variable. For example, we can look at the expectation minus the variance of it, which will guarantee that we have a small variability in our performance. But in general, if we borrow some ideas from the theory of mathematical finance, people have been thinking about how to design such statistics called risk measures in many different ways that can guarantee reasonable performance once you're unlucky with good performance once you are nominal. So different alternatives as to using just the variance or simple things like that. A different reason why we should care about risk is that our model about the world can be wrong. And as it turns out, in sequential decision making, a small modeling error can build up over time because we're looking at a sequential task and cause a very large gap in performance. So here we want safety against this model mismatch, or modeling errors. And a natural way to think about this or to tackle this problem is to look at it as a robust optimization approach and assume that there is some kind of adversary that can perturb our model about the world, and we'll try to find a policy that acts the best according to the adversary's worst case perturbation. This would guarantee that we don't make decisions that kind of rely too much on things that can errors that can build up over time. That will guarantee the adversary a lot of power. So in my PhD, we've worked on various reinforcement learning algorithms for these two types of risk scenarios. I won't go into all the details. I'll talk about my favorite result, which, as we made some more progress on these problems, we identified that actually both of these risk scenarios are related, and we can unify them under a single framework. And this framework is under a risk measure called conditional value at risk, or CVAR, which is what I'll talk about now. So CVAR is a risk measure that's very prominent in finance. It's useful against very extreme unlucky situations. So let's see how it's defined. So let's think of a random variable x, and let's denote by q alpha its alpha quantile. So for example, a 1% quantile is the number that you have exactly 1% chance of x being smaller than that number. The CVAR at level alpha is the expectation of x conditioned that it's smaller than the quantile. This means that we are looking at the average 1% worst cases that this random variable can take. So if we draw its distribution function, here q alpha will be the number that there is that once we integrate over this area, we get alpha. This is the alpha probability. And we're taking an expectation only in this part of the tail. So in CVAR MDPs, if you're looking at the reinforcement learning, we'll try to find a policy that maximizes the CVAR of the discounted rewards. Basically, we're looking for a policy that acts the best when it gets the most unlucky. So this won't care about the expected rewards. But you can add to this objective, for example, the expected reward to guarantee that when you are not unlucky, you still perform well. So CVAR is popular in finance mainly because it takes into account very rare but very bad outcomes that occur way, way left here in this tail. So they might have a low probability, but because we're taking an expectation of this tail, they get represented by the CVAR. But one very interesting reason to use CVAR, or a different reason, is that we can actually show that CVAR risk is also a measure of robustness. Remember, robustness, as I said, is being robust to perturbations of our model. So here's a result. Let's define the adversary's possible perturbations in this structure. So the adversary at each time step in our trajectory can perturb our transition probabilities, the model, by some multiplicative perturbation delta. But he can't choose any perturbation he wants. He has a budget. The product of all his perturbations in a trajectory must be smaller than some budget eta. So this means that the worst can happen at every time step. If, for example, he chose a large perturbation in the beginning, that means that he can't perturb much more at the end. Now let's denote by this delta the set of all possible perturbations under this budget. So our result shows that the CVAR with parameter 1 over eta, so the risk is inversely proportional, this number is inversely proportional to the budget, is exactly the worst case expectation under this perturbation model. So what does this mean here? It means that by optimizing CVAR risk, by being strong against unluckiness in this particular sense, we're also guaranteeing robustness against model perturbations. This is intuitive in a sense. It makes sense, right? Because if we find a policy that can handle any kind of unlucky noise in our system, it also makes sense that it will be harder to change or to make random perturbations to our model to kind of fool this policy. But this theorem shows or quantifies this exact intuition. And I think that this result is appealing because in many cases, both types of uncertainty are actually important, both unluckiness and modeling errors. So CVAR gives us a unified approach to dealing with both of them. If we can actually solve CVAR MDPs, we'd be guaranteed that our policies are robust. And the good news is that we can actually optimize CVAR MDPs. So our first, we have a result for the planning case where we know the model. There we have an extension of the value iteration algorithm where we need to add some linear programming and interpolations to solve CVAR MDPs. Our algorithm was the first to have error bounds and a convergence rate. I think it's the only one so far. And the idea is that by relating it to value iteration, we can guarantee the same kind of geometric rate by showing that it involves a contraction at each iteration. And we can also show that the computation required at each iteration is tractable. For the reinforcement learning case, we have an extension of policy gradient algorithms for CVAR MDPs, which is what I'll go into detail right now. And this is, for this course, this is the most compatible with deep reinforcement learning. I think this is what's be most useful for this class. So actually, let's go back again to the CVAR definitions. Oh, here I replaced CVAR with this letter phi, just to make it easier to write down the equations. So we would like to derive a policy gradient algorithm for this kind of CVAR for random variable. But before we begin, let's remind ourselves, how do we estimate the expectation of a random variable? That's easy. We just take the empirical average. How can we estimate the CVAR of a random variable? Well, the intuition here is that because we're taking an expectation over the alpha % worst cases, what we can do is just sort our data and take an average over the alpha % worst cases, worst examples in our data. This is kind of intuitive. And it's easy to show that this would converge to the CVAR just the same as the average converges to the expectation. Yeah?
In this case, so X here,
Yes?
when we actually use it, would represent like the reward that we get over time?
Yes, exactly. So X here would represent the reward of a trajectory. So the trajectory would be the random variable, and we'll be looking at the reward of that trajectory.
So in general, is CVAR usually related to like the worst event, like the worst events, or just the most unlikely events?
No, the worst events. So we specify worst by the reward that we get for that trajectory. So we're looking at the trajectories that have the lowest possible rewards. So if we assume that all we care about is rewards, then this would be the worst. Okay. So now let's recall how we the theory of policy gradient or the likelihood ratio method. So we want to estimate. This is for the standard random variable. We want to estimate the gradient of the expected value of x. So we know that we can just write this expectation as an integral over the probability of x times x. And then we insert this gradient into the integral. And then we do the likelihood ratio trick. We divide and multiply by the distribution f. And this is equal again to an expectation over the gradient of f over f, or the gradient of log of f. And once we have again an expectation here, we can approximate it using the empirical average. So now maybe you can guess what we can do to estimate a policy gradient for CVAR. I think that the natural answer here is if we want to estimate a likelihood ratio for CVAR, we should just take the average over this log likelihood over the worst cases that we saw in our data. And this looks very natural, but actually is wrong. So maybe you can guess why this doesn't hold. All right, so let's do the derivation again and see. So we want to estimate CVAR. CVAR is, we're basically taking an expectation only over the tail, up to the quantile, right? So we'll be integrating up to the quantile over the probability. It has to be normalized by alpha, because this is the area of this part of the curve. And once we take a gradient of this, well, we need to do it properly. So we need to take into account the fact that once we change the parameters, we can also change the quantile. This is called, I think it's called the Leibniz rule for derivation, integrating inside the integral. So what we need to also take into account is the change in q times the value at q. So we get this additional term. So this is what makes this naive solution actually incorrect. So as it turns out, we can still get a pretty simple formulation for CIVAR. We just need to do one more step. So let me actually do this on the board. So we have an integral 1 over f of x times x over alpha dx. And we saw that this equals, we want to take the gradient of this, and this equals integral from minus infinity to q of the gradient of f of x times x over alpha dx plus the gradient of q times f of q times q, right? Over alpha. But we also know that the integral for minus infinity to q of f of x times x, what does this equal to? This is just the area under that curve up to q. This equals alpha by definition, right? So we can take an integral, a gradient over both sides of this equation to get that. Okay, let's do this side. So we have an integral from minus infinity to q of the gradient of f of x times x dx plus the gradient of q times f of q. That's it. Oh, sorry. This is dx. My mistake. This is just dx. And this equals to 0 because the gradient alpha is just 0. So this is good because we have something like the term we have here. All we need to do is multiply this by q over alpha to get that the gradient of q, f of q times q over alpha equals minus integral from infinity to q, gradient of f of x times dx, times q over alpha dx. Right? So now we can plug this back here and get that this equals to the integral from minus infinity to q. Let's collect the terms. Gradient of f of x. This will be x minus q over alpha dx. Right? So what did we get here? We get that what we need is to subtract from our variable a baseline. The baseline is exactly the quantile, and then we get the policy gradient. So if you remember the standard policy gradient for the expectation, we can remove any baseline that we want and it will still be unbiased. But here we need to subtract exactly this baseline, the quantile, for this to remain unbiased. But it's very easy to use as a formula for estimation because estimating the quantile is easy. So here's the formula. Actually here we write the formula for the reinforcement learning case where, as you asked before, x is a trajectory and r is the reward of that trajectory. Very similar. But actually for deriving this equation, instead of 2 lines on the board, it requires something like 2 pages. It's slightly more involved because we can't use the standard Leibniz rule because we have the reward of a high-dimensional random variable. But intuitively, it's still the same. So this is the expectation, the standard policy gradient formula conditioned that we are smaller than the quantile with a baseline that is the quantile. So basically, the estimation algorithm would be very similar to what we thought. We average over, we sort our data samples or the trajectories, calculate the reward for each trajectory, sort them, and take only the alpha % worst cases in these trajectories, and remove this quantile baseline. Estimating this quantile is also easy. We just sort out the data and select the one at the alpha % element. So there's a small caveat in analyzing this policy gradient algorithm if you want to show that it's unbiased, because this quantile estimator is also a biased estimator of the quantile, which involves additional bias. But we can show that this bias is actually very small, and by using that, we can show that this will still converge easily to a local optimal solution. Now let's see an example of this. We applied this. This is joint work, by the way, with Jonathan Glasner and Shai Manor. And this is some of the results that I'm going to show now. And we applied this to the game of Tetris, where, well, this is slightly before the deep learning was very popular. Here we used linear features, which were kind of standard for this game. And the policy is just a softmax policy of these features. Here, like in the standard Tetris game, if you clear multiple rows, you get a bonus. So if you cleared 1 row, you get 1 point. If you cleared 4 rows, you get 16 points with a squared reward. And we compare standard policy gradient with this CVAR approach, which should result in risk-averse policies. So after we train the policy, here is the histograms of the rewards for the policy that we got. So in red is the standard one, and in blue is the CVAR one. So you see that the red one, the standard one, gets on average more reward. And it actually looks much better overall. So why am I showing you this? Actually, what we care about is what happens on the left tail here. So let's zoom in on that. And here is a zoomed in picture. And here you see that the standard policy gradient has much more dominance in these very bad cases. These are cases that you get very low reward, compared to the CVAR policy, which is much as dominant here. And if you compare the CVAR, indeed, our policy gets higher CVAR. But we can actually interpret what's going on here. Actually, can you guess what the risk-averse policy would do in a game of Tetris? How do you get not how do you not build robustness to unluckiness here? Yeah.
So I guess there's a strategy, right? You build up your field so that you can install 4 rows at once, which is more risky because it builds up your stack higher.
Exactly. That's exactly the solution. Yeah. So let's see. So we can actually show this, so that this is what it learned. So this is a linear policy with where the features, well, these are hand-selected features, these standard ones. And if we compare the weights that both of these policies learned, we see that the biggest difference is something called a board well, which is exactly as you said, is a narrow gap in this board. So the standard policy will kind of build these gaps because it will wait for these shapes which generate high reward. CVAR tries to avoid it. Here's an example of this in practice. You see the risk-averse policy on the left. This will be an unlucky instance. And you see that the standard policy here will kind of wait for this long shape that never comes, which causes it to lose the game. The children here, by the way, are Jonathan's children, who, if you're wondering. So let me conclude this part of the talk. The risk-averse reinforcement learning offers a unified approach to safety, both to unluckiness and to model mismatch. We have efficient algorithms for various types of risk. I've talked only about CVAR here, but we can also do mean variance and coherent risk. And turns out that many RL algorithms can be extended to these cases. And there are various applications of this. Finance is probably the most common. Many models in finance require sequential decision making. For example, trading with options. But also in robotics, now people are looking into transfer from simulation to real world. And obviously, the model that you train in simulation will be different than the real world. And one idea is to train risk-averse policies in simulation so that this transfer will go smoothly. And there is some recent work on that using something like the CVAR. So now, the next part of the talk, let me tell about the work I've been doing here at Berkeley. And this is joint work with you, Garrett Thomas, Sergey Levin, and Peter Abil. So as you know, in the last 2 years, there's been quite a lot of progress in deep reinforcement learning using deep networks in RL. This work maybe provides a bit of insight on how to apply deep learning to the reinforcement learning case and why it can be different than, say, image classification, where these methods originate. So our general goal is to build autonomous robots. We'd like the robot to, we'd like to tell the robot, bring me some milk from the fridge, and it will go and see something like this and understand where the bottle of milk is and how to get it. So the challenge here is that the fridge looks different every day, which requires generalization. While it's very easy for us to do this, we do this every day. For robots, this is quite hard at the moment, at least. But we believe that reinforcement learning could get us there. And the reason, which is probably the motivation that you're taking this class, is the very recent successes of deep reinforcement learning in learning complex decision making directly from raw visual input. For example, the DeepMind work on Atari, or the work done here at Berkeley on object manipulation in robotics, and many other works recently. But one perhaps surprising fact about many of these works is that the network architectures that were used are actually very similar to network architectures for image classification, and consists of a few convolutional layers followed by a fully connected network layer for selecting the actions. And we call these networks reactive in the sense that they select the actions directly based on features in the image. Now, we know that these networks are successful for complex tasks. We've seen them work on Atari, on robots, but can they understand? So what does this mean to understand? Let me answer this with an experiment. A very simple experiment on probably the simplest RL benchmark, the grid world. Here the goal is to navigate this discrete object between these goals, between these obstacles to some goal. And we actually make this super simple. We let the agent observe everything. It sees the map, it sees its position, it sees the goal. Only thing it needs to learn is which actions to select. And we trained a reactive policy to solve this task. That was easy. Obviously, it succeeded. This is way easier than learning to play Atari. But then here's the thing. We then trained a single policy to solve various instances of this task with random obstacle positions and goal locations and starting positions. Now, we expect that if the network understands anything about this task, it should also be able to solve an unseen map with different obstacle positions than what it trained on. And going back to the refrigerator example, this is the generalization we expect just from understanding what the task is. And well, if you look at it, it requires just a glance to understand what the solution here is. And to our surprise, we found that these reactive policies really don't generalize well. They easily solve the training domains, but fail on the test cases. So why don't these reactive policies generalize? We understand that solving this task requires sequential decision making, which in generally involves or requires some planning computation, for example, value iteration. But actually what we do in reinforcement learning is getting around that. We don't do planning. What we learn is mapping from states to good actions in our training domains. How these good actions are obtained depends on the specific algorithm that we're using. So for example, if you're doing Q-learning, we'll be learning how to map states to Q values. Q values represent a long-term consequence of an action, something like a plan. If you're doing imitation learning, then an expert does the planning, tells us which action to take, again on the planning domain. If we're doing a TRPO or policy gradients, then we're choosing actions that lead to high advantage, which is again a sort of planning. But the point is that all this planning is happening implicitly by the algorithm, or explicitly, in the case of the expert, and on the training domains, and all the learning that's taking place is here in this error. Again, from states to actions on the training domains. Now, what happens when we see a new task? We need to replan. But we never learn the planning part. And it might be that our networks are perfectly expressive enough to represent this mapping from states to good actions on the training domain, but not expressive enough to represent this planning computation. So let's see how we can design networks that have the capacity to do this planning computation, and we'll see that they indeed generalize better. So let me present the model. We would like a network that can learn to plan. So let's start with a reactive policy, because this is what we know how to design. And we want to add a planning model that takes as input the observation, decides on some planning computation to do, and then transfers somehow this plan as additional input features to the reactive policy. So now the challenges of what we need to answer is, what do we need in order to define a planning computation? How can we plan? How can we use this plan with the reactive policy? And how can we learn all of this? So let's start with the planning. We've already seen a planning algorithm, the value iteration algorithm, where the idea was to define this value function, which maps states to their long-term value. For example, in this grid world, value can represent the shortest distance to go from a state. Yeah.
Can you explain again what a reactive policy is?
Let's think about it as a shallow network in our terms. So most of the, for example, in the Atari games, they use, I think, 2 or 3 layers in the network. And basically, most of the results that I've seen in RL don't use more than, say, 7 or 8. Yeah. So here it could be the shortest distance from a state to the goal. But in general, we talked about maximizing the sum of rewards from a state to the from a state. Now, we know that once we've calculated a value function, that's sufficient for a reactive policy to make optimal decisions. So in that case, the reactive policy is a very simple policy, just the greedy one that chooses the maximum value. We've seen it in the beginning when we talked about value iteration. So this is good, because eventually we would like a reactive policy to take the decisions. So we know exactly what information we need to pass to it. So how can we calculate this value function? Let's again look at value iteration algorithm, which I've written again here. At each iteration, we go over all our states, update the value by maximizing over the actions of the current reward plus the next value that we get. If we think about it, how this looks like in this grid world example, for each state or each pixel in this map, we'd be looking at the distance to the neighbors plus what we think is the distance from each neighbor to the goal and maximize over that. If we have stochastic transitions, we'll need to multiply the value of each neighbor by the probability of reaching it. Now, this drawing looks kind of similar to how we draw convolutional neural networks. And the reason is that actually mathematically, the computation that we do in value iteration is very similar to the computation that's going on in a convnet. For example, in this 2D grid world, it's very easy to see this. This expectation of reward plus next value can be seen as a convolution, where the convolutional kernel, the weights, are just the probability distribution in this expectation. So we can think of it as transferring the current value estimate and reward by a convolution to get a hidden layer where each channel in the CDN layer corresponds to something like an action. Then this maximization over actions is similar to max pooling in a standard ConvNet. The difference is that we're not using max pooling to reduce the a spatial dimension of the image. We're pulling over the channels here, or the actions, to get another value function, which is of the same size as the original one, but passed through this Bellman update. And we can repeat this iteratively by feeding in the newly computed value function as our input here. And what we get is a deep ConvNet. The depth corresponds to the number of iterations we take in the value iteration algorithm. And the weights are shared, just like in the because these weights correspond to this expectation here, which remains the same. So in general, well, this is easy to see for this 2D case. Oh, yeah, question.
So this is being done for as just substitute value iterations or on top of value iterations?
This is, we're going to design a standard neural network, a policy for reinforcement learning, that does a computation that's similar to value iteration. So we're not going to do value iteration explicitly at any case. We're going to use our knowledge about the computation done in the planning algorithm of value iteration to design our neural network for a policy. So yeah, so this was very easy to see for this 2D case, but in general, we can think of an expectation as a linear operation that we apply to each state in value iteration algorithm, just like a convolution, and a maximization followed by a maximization like max pooling. So this analogy is actually more general. So we're going to use this analogy between the value iteration algorithm to design a neural network that can actually plan. So let's go back to the scheme we had before. We want to take in the observation and define a planning computation. So we know what we need in order to define a planning computation. We need rewards and transitions. So for the reward, we can just take a standard mapping from the observation to some reward function. For example, a standard ConvNet. For the transitions, we saw that they can just be represented as the kernels in the value iteration algorithm. So to do the planning, we will use exactly this value iteration algorithm, which is just a ConvNet, as we've seen. And then we also understand that the value function that we get after planning is all the information we need for a reactive policy, say a shallow policy, to make optimal decisions. So we can just take a vector of all the values that we get after performing this iterative value iteration algorithm and add those as additional features for our reactive policy. We can actually do a little bit better. We also add some form of attention here by noting that, for example, in this grid world, we don't need all the values. We just need the values of neighboring our states in order to make decisions, which makes learning here more effective. So now, how do we train all of this? One idea is to know that each block here is just a neural network and train it separately. But that will require supervision on each block. Our main idea here is that we can look at this whole policy or whole neural network as just one deep neural network that maps from observations to actions. This goes from observation to some planning computation, a differentiable planning computation because it's just our ConvNets, into an action. So we can think of it as just another neural network representation for a policy and train it end-to-end from observations to actions like any other policy in reinforcement learning. So let's emphasize what we'll be learning here. We'll be learning how to map an observation onto a relevant planning computation, one that produces relevant actions to make predictions. So let's see how this works. Here's again this grid world domain. Here we trained using supervised learning or imitation learning. The expert here is just a simple Dijkstra algorithm for computing the shortest path. And our data consists of these random maps, a position on this map, and the direction of the shortest path to the goal from that position. And we compare value iteration networks or VINs with two ConvNets that are inspired by state-of-the-art results. One is a ConvNet similar to the one used for playing Atari. Another one is a fully convolutional neural network used originally for semantic segmentation. This is kind of similar to a semantic segmentation problem where you can think of each the direction of each pixel here to the goal as the label of that pixel. Since this is supervised learning, we can directly measure the prediction error for our actions at each state. And this is on a test set, standard supervised learning error. And we see that, well, all of these networks behave rather similarly. The error increases as we increase the map size. But actually what we care about is not the single state prediction error, but how well our policy behaves. Once we use it as a policy, unroll it from a state to the goal, does it reach the goal and not hit obstacles or not? And once we measure that, we see that these reactive baselines really perform poorly once the map size increases. So the intuition to what's happening here is that these baselines kind of learn to memorize the good trajectories that they've seen, which works well on a small map because there's not much variation that can happen. But this really doesn't scale well to large maps. Value iteration networks, on the other hand, learn the underlying planning computation that requires to produce the actions. Here's an example of the trajectory that our networks produce compared to the optimal shortest path. It's not the shortest path, but it's definitely a short path between obstacles to the goal. We can actually interpret what's going on here. Because we know we designed the network as a planning computation, we can actually query the specific parts and understand what's going on here. So for example, we can query the reward part and see what reward mapping this network learned from this image to reward. And you see that it learned to give a high reward at the goal, a very negative reward on the obstacles, and a slight negative reward on all the free spaces. This makes sense because this induces a short path to the goal. We can also visualize the value that it learned after being passed through the iterative convolution layers. And you see that, well, the value of the target is high. And in general, the gradient towards this point, or the gradient of this value function points towards this goal around the obstacles, for example, as you see here. So this makes sense. So interpretability is important, and we can get that here for free. So you might ask, is it only the fact that we trained a deep?
Yes, nice.
Yeah.
So in the previous slide, that image is, so this is like a new image, and you're looking at what?
Yeah, so this is the input. This would be the input to the network.
But it's like something you haven't seen, right?
Yeah, not seen during training.
That's like the reward that it outputs from.
Yes, this is the reward that it outputs. There was a mapping from this image to reward. This is what it outputs, and this is, yeah. So again, our networks, the VINs are much deeper than the reactive baselines. So you might ask, is it only depth? Could we, if we train deeper, would we get the same effects? So what we did is we just untied the weights in the value iteration network. We just makes it a very deep ConvNet. And this resulted in worse performance, especially with less data. So it's not only depth. The structure of the value iteration network here actually was important. And we can also train it using reinforcement learning instead of supervised learning. This is an example using TRPO. And you see that we get, here we measure different than the standard graphs that you usually see for reinforcement learning. This is success rate on a set of test domains, not on the training domains. And you see that we get much better performance here. But the really cool thing about value iteration networks is they're just neural networks. So we can easily compose them with more complicated structures for perception and control. For example, here we replace the synthetic grid worlds with a natural image of a terrain. Here it's a Mars terrain. And the goal here is to navigate between these craters. Only thing we needed to change is kind of beef up this mapping from image input to reward. And here's an example trajectory in purple of what it predicted compared to the shortest path in blue. Here's a different example. This is a continuous control domain. We need to move this red red ball, which has now mass and inertia, and navigate between the obstacles. It can bump into them and stop it at the goal. Now, you might ask, how can you use discrete planning, value iteration works on discrete spaces, in this continuous domain? So our idea was to kind of let the network figure it out by itself. We use the same architecture, grid world architecture that we saw before for the grid worlds. The input is just a low resolution image of this map. And the reactive policy now takes into account both the value function from this grid world and the continuous state and velocities. The idea here is that while planning on this grid world is definitely not sufficient for solving a task, for example, it can't handle velocity or learn to stop it at a goal, the reactive policy can integrate kind of a rough path in this domain, a rough trajectory, and learn to track it using the continuous variables. But this will all be learned. We don't need to specify or teach it anything. It's trained end to end. So here's an example. We compare it again to ConvNet, one that was recently used for solving such continuous tasks. And we see that we learn a much more sensible trajectory. This is on a test domain that wasn't seen during training. And here's some video of it in practice. This is the same network being applied to multiple domains that were not seen during training. See that it mostly generates reasonable performance. Sometimes it fails, but mostly it learns to navigate around obstacles to the goal. Let me just say we applied value iteration networks to other types of problems. For example, navigating websites to find some query page based on planning on a graph. This was not a grid world. And also we can compose value iteration networks hierarchically by noting that once we have a value function, we can just use it as an additional reward channel. Now we can think about value functions as just channels in an image. And we can think of a value function of one VIN as an additional channel in the input to a different VIN and concatenate them together like that. I've shown you several variants of navigation from an overhead map, which contains all the information we need in order to plan. So now you might ask whether we can apply these ideas to domains where we don't have the full information to define planning. For example, a first-person navigation. So there is some follow-up work done by the group of Jitendra Malik and led by Saurabh Gupta that learned both mapping and planning for first-person navigation. So the idea that they used is to have two parts to the network. The first part is a mapper model, which transfers the first-person image onto a memory of the map of the world. And then you use the hierarchical value iteration network to plan on this learned map, outputting an action. So they have an end-to-end network from a first-person viewpoint to the action that involves both planning and mapping. And here's an example video of their approach, learning to navigate directly from person view. This is on a building that it hasn't seen before. It's trying to navigate to this place. And I think this is very cool. Okay, so to summarize this part of the talk, the take-home message is by learning to plan, we can get better generalization in sequential tasks. Value iteration networks is one neural network that has this capacity to do planning. We've seen it by relating its structure to a well-known planning algorithm. One challenge that we have, though, is how to apply these ideas to problems where the underlying planning involves a high-dimensional state space. So for example, low-level robot control, we can't really map it to a two-dimensional or three-dimensional grid to apply value iteration on. So in the next part of the talk, I'll tell you about how we can extend these ideas of combining neural networks with a known planning computation to continuous control. And this is based on hindsight. This work is hindsight MPC. This work with Garrett Thomas, Tianhao Zhang, Sergey Levin, and Peter Abil. The motivation here is to solve problems of robot manipulation, for example, assembling these gears. The challenge, as I said earlier, is that we don't have accurate physical models, and the dynamics also involve friction and contact, which is challenging. We build on a well-established control method here called a model predictive control, which was recently used for this manipulation task by combining with adaptive model learning. So before I tell you about our method, let me explain how this adaptive MPC works. So adaptive MPC is an online control method. Let's see how it calculates the control at time t, where the state is xt. So the first thing we do is use a model that we have about the dynamics to predict how that trajectory will evolve in the next h time steps. We use our current model for it. The model is not necessarily correct, but we update it as we go along. Then we use this prediction to linearize the dynamics model around this prediction. And then we solve an optimal control problem on this h time steps. This h is the horizon of the algorithm. So the idea is that once we have linear dynamics, we can solve a standard optimal control problem. Specifically, if the costs are quadratic, which is what we used, this is something called a linear quadratic regulator, which you've seen already in this class. So in linear quadratic control, we try to minimize the sum of costs. So cost is quadratic, so it would be a quadratic function of the state plus a quadratic function of the action under linear dynamics. And as you have already seen, we can solve this optimal control problem using dynamic programming. And the optimal controller turns out to be a linear function of the state. The gains in this linear function can be calculated iteratively using the Riccati equation, which is going from the last time step in the horizon back to the first step, and doing this series of matrix multiplications and inversions. So once we've done this computation, we have the optimal policy for horizon h. But we only execute the first action in this horizon, and then observe the next state that we reached. Now we have more data because we've seen another transition. We can update our dynamics model, and we repeat this. From xt plus 1, we again plan for a horizon of h, take the first action, replan, and repeat and repeat and repeat. So this procedure in general works really well, and it has applications in many areas from control to chemical process engineering. But there are still two suboptimalities of this process. One is that the prediction we are using to linearize the dynamics is based on some inaccurate model, because we don't know it. And actually, predicting, for example, when a contact will happen is quite challenging. The second reason for this being suboptimal is that we use a short horizon for doing the optimal control problem, and not the full horizon, which we actually care about. And typically, we use a very short horizon for two reasons. One is that we need to compute this online, which is demanding. And also, if we don't have the accurate model, there's not really any sense in planning too far ahead with it. So our question was, how can we improve MPC in a case where we can repeat the same task multiple times? This is an iterative control setting. Let's say we're doing this assembly task. We can try assembling the gear several times before we need to succeed. So how can we learn throughout the process? So one naive solution is just to say, OK, we're training more times. We'll have more data. Our dynamics model will be better. That's true. And we tried that. It actually didn't work so well. It didn't really give any significant improvement. So now let me tell you about a different approach. Our idea that we call the hindsight plan, or hindsight planning, is the following. Let's say we've executed a trajectory. We saw what happened. Now we can go back and ask ourselves, well, I know what I planned. I know what actually happened. How would I have acted differently knowing what actually happened? More specifically, we can go back in our computation to time step t. But now we're doing this offline, so we know how the trajectory actually evolved. We have a better dynamics estimate. And we're going to recompute the calculation for the action at time step t. But now we can linearize on the actual trajectory, not on some prediction. And we can also use whatever horizon we want in the optimization, in the online control, sorry, the optimal control problem, because we're not limited by real-time constraints. So after we do this, we get a new action at time step t, call it u bar on the hindsight action. And we can repeat this for every time step in our trajectory, getting something that we call the hindsight plan. Now, these hindsight actions essentially mitigate the two sources of suboptimality about the prediction error and the finite horizon, or short horizon. So in principle, they are better. We would like to use them. But we have a problem. We can't really use them in the next MPC rollout because, again, MPC will still use a short horizon. So how can you use them? So our idea is to treat them as like a teaching signal, like an expert, and do something like imitation learning from these hindsight actions. Basically, we're going to change the cost of the online MPC such that it produces actions that are more similar or mimic these hindsight actions. And this will result in a policy improvement. More specifically, let's write down the original LQR cost. The LQR cost is some quadratic distance to some goal position plus a quadratic cost on the actions. We're going to change this and assume that the target position or the goal position is some neural network output. It takes as input the current state and some parameters theta, the weights, and outputs the goal at time step t. This would be a shaped goal where the intuition is that we can use this to learn something like a waypoint for the algorithm, a goal that depends on the current position. And going back to our general approach, this is another instance of combining a well-understood control algorithm. Here it's LQR and MPC, with a black box neural network as input. Here it's inputting the costs for this MPC. Now, we want to make this cost, or the online MPC, mimic the hindsight plan. So here's a natural cost function to minimize. We would like to make the actions that the short horizon MPC with a cost function with parameters theta, we want to make that similar to the hindsight actions. So here, the first term is what happens when you do online short horizon MPC with this neural network with parameters theta, and the second term is just the hindsight actions. This might look simple, but actually, to optimize this cost, we'll need to differentiate so the whole computation of the online MPC. Right? We need to differentiate through the dynamic programming LQR computation that we saw before, the matrix inversions and multiplication. But actually, we can do this. And well, in principle, this could have done earlier, but we're actually exploiting software like Tiana and TensorFlow that makes this much more manageable. So we can minimize that objective, and we get, weights for a neural network that learns some cost shaping that makes the short horizon MPC behave like long horizon planning. Let's see an intuition to what we expect here. Here's a task where we need to move this yellow ball through this opening towards some goal position. So what would standard MPC do here? It would try to directly navigate to the goal, because the limited horizon doesn't take this obstacle into account. Only after hitting it, it will kind of navigate around it. What we want to learn is to directly go, or shape the goal so that we directly go through this opening towards the goal. So here's an example of this. So first we show the performance of the original MPC, and as we expected, it first kind of hits this obstacle and then navigates to the goal. Our method very quickly learned a cost shaping that makes the original goal more to the right, such that it navigates through this opening and then reaches the goal. So this is after 3 iterations. Here's a more challenging task. This is peg insertion on a 7-degree freedom simulated robot arm. We need to insert this peg into this hole. I don't know if you can see it. This is a more challenging. The state space here has 26 dimensions and 7 action dimension. Definitely not something that you can solve using discretization. The dynamics here are, this is similar to GPS, ILQG works. We learned the Gaussian mixture model dynamics for this. We learned it on a free space, and we use online adaptation to account for the dynamics, or for the obstacles. And first, here's the results. First, we show the MPC, the standard MPC plot here in red. It's already quite reasonable. It learns to solve. It starts out by solving this test. It starts out by inserting this peg, and this is good. I mean, we started out by knowing that MPC is a good approach. That's what we want to build on. But we also want to improve the results. So what we measure here is the minimum distance to the goal. And you see that our method really quickly improves upon MPC. We also compare to a state-of-the-art model-based learning, which is ILQG. ILQG takes into account the full horizon, which this could be seen as the best we can do in this task. But it takes much more samples because it needs to learn the whole model, the dynamics model as well. Yeah.
Why is FPC not really changing?
As I said, updating the dynamics model really didn't make a significant improvement. This is what we started out. This is the initial thing we tried out, and from that we moved on to the hindsight planning because it made much more significant improvement. Here's a similar task on a PR2 robot. Here the task is to insert this small wooden peg into this hole. This is the original MPC. Very much like the illustrative example, the 2D example, it kind of first hits this plate and then inserts it into the hole, while our method quickly learned a smooth and direct movement. So to conclude, our approach is to combine well-understood algorithms for control we have decades of research on with expressive black box neural networks. Here we gain both from understanding the algorithm or using a simple algorithm that we understand, plus the very expressive capability of neural networks. We can see it as designing a neural network architecture that has an inductive bias towards a control solution. And this is good because we want to solve control tasks in reinforcement learning. I think this is a more principled approach to network design than just choosing a very deep neural network and hoping for the best. We've seen that this leads to better generalization and also that it promotes some new algorithmic ideas like the hindsight MPC. As I said, we can look at this approach as just adding inductive bias to our neural network, inductive bias towards control. And in this sense, it makes sense to compare it with other approaches in the literature. So on the one hand, we can think of completely model-free RL that just uses deep neural networks or memory-based neural networks and trains them. They have been shown to perform very well on the tasks they are trained on. As we've shown, this doesn't really generalize well to changes in the task. Model-based RL has the opportunity of being completely generalizable because if you have a good model of the environment, you can solve any change in the task. But it's kind of difficult to learn good model-based models in model-based RL. There's been some interesting work called Embed to Control that tries to learn linear models for the task and then use optimal planning on these linear models. And inverse RL tries to learn just the reward function for the task. So you can think of all iterations as something like an inverse RL architecture where we learn both the dynamics and the reward in the supervised learning case. It's also related to other types of neural networks for learning algorithms. We learn planning algorithms. People have been designing neural networks, for example, like the neural Turing machine that can learn any algorithm, or divide and conquer neural networks that learn dynamic programming. Iterations networks learn a specific planning computation, or we exploit the fact that we know exactly what computation we need to solve the task. Very similar is the backward Kalman filter, which does this for the Kalman filter computation. That's it. I'd like to thank my collaborators on these projects. and also some funders. Thanks.
Okay, we have a few minutes for questions for Pete. So if anybody would like to ask a question, please raise your hand.
Yeah.
So unlike value iteration networks, it looks like hindsight MPC is very much task specific. So if you change, for example, the configuration of obstacles in your problem, your algorithm will probably need to retrain, right?
So that depends on how you design the mapping from observation or states to cost. So if, for example, this is the neural network, right? So if you train this neural network to map from, say, an image of the obstacles to the cost, it will have the capability of generalizing on that. What we did test for generalization is the initial position that we start from. So in that 2D example, we trained on, say, 4 or 5 points, and we tested on many different other points that we haven't trained on, and we saw that it generalized well. It generalized well, I mean that it gave a better solution than what MPC would have given from that same points. Those same points.
Okay, well, let's wrap up then. And just to remind you, this Wednesday we'll have another guest lecture from Hong-Lak Lee, who will come by. He's a professor at the University of Michigan, currently at Google Brain, so he'll come by and give a talk. And then remember to check Piazza for the instructions for your milestone presentations as well.
Noise.